to OneClass. My name is Jeff Krause. I have a PhD in physical chemistry, and today I'm going to go through a few undergraduate level to high school level physics questions. So here's our first one. We have two-dimensional dynamics. Which often involves solving for two unknown quantities and two separate equations. We have a block, which we have no figure, but I'll just draw it. It has a mass of 10 kilograms, is being pulled by a force on a table. So we have a block, 10 kilograms, and we're on a table. And we've got some friction force in which mu is 0.3. There's four forces acting on it, so there's an applied force which is angled at 30 degrees. We've got our force of gravity and a normal force. And this is our static friction. So the box isn't moving. And we want to find the force necessary to just overcome our static friction. So we need to look in all directions, or right now we've just got x, y. So first let's decompose our applied force. So that would be, we've got this 30-degree angle. And so if this is force applied, then this is force applied cosine of 30. And this is force applied sine of 30. Okay? And so we can write that our applied force in vector notation is the force applied times cosine 30 in the x-hat plus force applied sine 30 in the y-hat. Okay, and now we can see that all the other forces, so our frictional force is going to be in the x direction, and each of the others are going to be in their own respective direction. So if we look in just the y direction, then we've got a positive normal force minus our mg force, and then plus our force applied sine 30, and then that equals 0 because MAY equals 0 as the acceleration is 0. So we've got no acceleration, so that'll equal 0. We can solve for our normal force as mg minus our force applied times the sine of 30. Okay. Now the reason why we would solve for our normal force is because our frictional force is always given by our coefficient of friction times our normal. So in this case, it is given by this. Okay. Now, if we look in the x direction, we just have the x component of our applied force and our static friction. So we just have our applied force times the cosine of 30 minus our static friction, and that equals 0. So then our applied force cos of 30 minus our static friction equals 0. And then we're looking for our applied force such that we just overcome our static friction, so that will be the solution to this equation. So now we need to collect terms here. So we've got f applied cosine 30 plus mu s sine 30 minus mu s times mg equals 0. Or rearranging, we've got that our applied force is equal to mu s mg over cosine of 30 plus mu s sine of 30. And now we have actually all those values, so I guess we might as well solve for what our applied force is. So that would be 0.3 times our mass, which is 10 kilograms, times our g, which is 9.8 meters per second squared, over cosine of 30 is a half. Nope, cosine of 30 is root 3 over 2 plus 0.3, and sine of 30 is a half. So I actually didn't do this, so I'll just do it now. So that's our denominator. So this is 28.94 newtons. All right, so there's our applied force such that we just overcome our static friction. Okay, so if we check through the solution here, so we've got two equations, rearrange, we eventually come to this equation, which looks the same, and they actually didn't finish it either. I'm just going to say its final solution, f equals 28.94 newtons. Okay. All right, so now we have a block with mass 14.2 kilograms. Now it slides down an incline. All right, I'm going to draw the incline like this. 37.7 degrees. I'm going to define my x and y axes as up the slope and away from the slope like that. And so now I've got a mass that slides down the plane with a constant velocity. And then it's projected up the same slope with an initial speed of 4.70 meters per second. And it asks how far up the slope will it get to before it comes to rest. Okay, so drawing our forces on here. I'm just going to redraw everything. So we've got our mg, our normal force, and in the first part, our frictional force is going to be this way, as it's sliding down the slope, and then it's going to swap directions. But let's first do the first part. So we've got a frictional force going this way, and it says that our velocity is constant, so that means that our acceleration is 0. So now, first of all, let's decompose the mg force. So our mg force is here. That is going to be our 37.7 degrees. And then, so then this guy is going to be mg sine 37.7, and this guy here is going to be mg cos 37.7. And if as my axes are xy, then this guy is x and this guy is y. So looking in the x hat direction, or actually, sorry, looking in the y hat direction, we've got our normal force minus our mg cosine of 37.7 is equal to 0. So then our normal is mg cosine of 37.7 degrees. And now looking in the x direction, we've got minus mg sine 37.7 plus our frictional force. So the way I've drawn it, the frictional force is in the positive x direction, is equal to 0. So then our frictional force is mg sine 37.7 degrees, which is 14.2 kilograms times 9.8 meters per second squared times sine of 37.7 degrees, which is 85.1 newtons. Okay. So it turns out I didn't need to solve for the normal here because I could use that to solve for a coefficient of friction, but our frictional force is always going to be the same. Because our frictional force, well, it's not always going to be the same, but it's going to be mu n, and as long as our normal force doesn't change, then it will be the same. And because it's the same block being pushed up the same slope, we will have the same normal force. But just to confirm that, so our normal force here is mg cosine of 37.7 degrees. And now if we look at the case where the block is going up the slope, then frictional force acts downward, our mg is downward, and our normal force is this way. Again, going x, y, same axis. Our mg is going to decompose the same. So our mg is going to give us mg cos 37.7 here, and mg sine 37.7 here. So then if we look in the y-hat direction, we've got our normal force minus mg cosine of 37.7 is equal to 0. So then our normal force is mg cosine of 37.7 degrees. So our normal force is the same, so our frictional force is going to be identical. So now looking in the x-hat direction, we have minus our frictional force, because it's now in the minus direction, minus our mg sine 37.7 is equal to 0. But we already solved for both of these, so our friction was mg sine 37.7. So both of these are just 85.1 newtons. So then together, they're, what did I get, 100? Oh, whoops. So they don't equal 0 this time, sorry. They equal our acceleration. So they equal max. And so then our acceleration in the x direction is then minus, what is that, 170.2 over our mass, which is given as 14.2 kilograms. So then this equals minus 11.986 meters per second squared. Okay, so then there's our acceleration. So we're given our initial velocity is 4.70 meters per second. So this is in the x-hat direction. We're going to take our initial position as 0, and we're solving for our final position. So we've got xf is equal to xi plus vit plus 1/2 a t squared, where that's 0. We also, its maximum position is going to be where the velocity comes to 0. So we've also got that Vf is Vi plus At, where that is not 0, that's 0, sorry. So then our T is minus VI over A. We can go ahead and plug this into our XF expression. Actually, it looks like I solved for it, so I'll just do that anyway. So it's minus 4.70 meters per second over minus 11.986 meters per second squared. So 0.392 seconds. And then plugging this into our XF expression, 4.70 meters per second, 0.392 seconds, plus 1/2 minus 11.986 meters per second squared, 0.392 seconds squared. And we get 1.8424 minus 0.9215. These are in meters. So 9209 meters. So that's how far up the slope we reach. Checking through our solution. You can compress all this obviously by subbing in the time, which is what they've done here. And they get a final distance of 0.92 meters. So that looks good. Okay. All right, so here we've got 3 circuits powered by identical batteries. And each contains differing resistors. So by Ohm's law, we have V equals IR, or I equals V over R. That means that our current is going to be inversely proportional to our resistance. So the greater the resistance, the smaller the current. So if we have 3 circuits with 3 resistances, so RA is 47 ohms, RB is 22 ohms, and RC is 56 ohms, then these are in the order of RB is less than RA is less than RC, and so then IB is going to be greater than IA is going to be greater than IC. And so that's our ranking from largest to smallest. Checking our solution here. That's basically what they have there. So that looks good. Okay, so we've got an egg is thrown vertically upward near the corner of a tall building. So it flies vertically upward, and then it goes back down. And so it says it just it passes a point 50 meters below its starting point. Five seconds after it leaves the thrower's hand. So it goes up and then comes back down. And so it reaches this point at t equals 5 seconds. So the egg is initially thrown upwards with some velocity. So we're looking for its initial speed for A. So our acceleration is minus g in all cases. So we can use xf is xi minus vit plus 1/2, or plus vit plus 1/2 a t squared. Our initial velocity is what we're solving for. We'll call xi 0. In this case, xf is minus 50 meters. And it equals our vit. So our t is 5 seconds plus 1/2 minus 9.8 meters per second squared times our 5 seconds squared. And so then our vi is minus 4.9 meters per second squared plus this actually times 5 seconds squared minus 50 meters all over 5 seconds, yeah, which is equal to 14.5 meters per second. So there's our initial speed. And now how high does it rise above its starting point? So that would be solving for where VF equals 0. So VF equals VI plus AT. So then T is equal to where VF is 0. So T is minus VI over A, which is minus 14.5 meters per second over minus 9.8 meters per second squared. Our negatives will cancel and get 1.480 seconds. And so we can use this to solve in our XF expression. Oops, it's a lot of extra pluses there. VI t plus 1/2 AT squared. Again, our xi is 0. And we know everything in this equation here, so our VI is 14.5. The time we're using is 1.480 seconds. This is negative 9.8 meters per second squared. So this equals 10.727 meters. Okay. So then the next couple questions are kind of funny. So its magnitude of its velocity at the highest point, well, we assumed it was 0 to solve it, and it would be because that's its turning point. So V is 0, and the magnitude and direction of its acceleration, well, A is minus G, so its magnitude is 9.8 meters per second squared, and its direction is downward. So I'm just going to check real quickly how this is going. Okay, it's kind of giving me a notice there. Okay, so that's that. So checking through the solutions here. So we get 14.9. So for some reason they used minus 48. I don't know why that would be. So it says it's 50 meters below its starting point. So that to me is minus 50. So I don't know why minus 48. And then, so that kind of throws off everything. So I'm just going to say distance for A. And I can't think of any reason why it'd be negative 48, so that's what I'm going with. Alright. Okay, so you are working for a summer. Your research director has devised a scheme for trapping particles. So we have a large sphere of radius r, or radius a. With a small tunnel drilled through the middle. So it's radius a. And here's our two particles, which are trapped at a distance of r from the center. And the particles have a charge q, and the whole sphere has a charge q. Okay, so this is an application of Gauss's law. So Gauss's law is just that our electric field times our area is the charge enclosed by the area over E naught. So for the first part here, our area is just going to be the surface area of a sphere which encloses the charges. So our surface area is 4 pi r squared. Our charge enclosed, so it's a uniform charge density. So our charge enclosed is our rho times our volume, which is rho times 4/3 pi r cubed. So that our electric field is rho 4/3 pi r cubed over 4 pi r squared E naught. We can cancel much of this and get rho r over 3 E naught. Our rho is our charge density, which is our total charge over our total volume. So then putting that into our electric field, we get charge R over 3 E naught times 4/3 pi A cubed, so the 3's will cancel. And we get QR over 4 pi E naught A cubed. So that's our electric field at a point R. So then our force on a charge Q is just QE. So that'll be QR over 4 pi E naught A cubed. So that's our force on a charge. We have two of these charges at distance 2r from each other. So then we also have our charge force, which is Q q over 4 pi epsilon naught r squared. In this case, our r is 2r. So if we look at the figure, so our charge repulsion is Q1, Q2, and both have a charge. I should put these in here just to differentiate a little bit. So both charges have Q1 is equal to Q2 is equal to Q. So our charge repulsion is then just Q squared over 4 pi epsilon naught times 2r squared. Okay. So then our net force is the sum of these two. So Q r over 4 pi epsilon naught a cubed plus q squared over 4 pi epsilon naught times 2r squared equals 0. So it equals 0 if they're in equilibrium. So we're asked to find equilibrium values for r. Equilibrium values for r. So now we need to rearrange things. So first of all, we can get rid of a q, get rid of a 4 pi epsilon naught. So that'll help a little bit. So then let's migrate some things and expand some brackets here. So we've got q r over a cubed is equal to minus q over 8, sorry, not 8, 4r cubed, 4r squared. So we're now bringing the r's around, so r cubed is equal to minus q a cubed over q. And so r is minus q a cubed over q to the 1/3. So now this is a negative sign, meaning that our radius would be negative, so that's not possible. So only positive for q less than 0. So our big Q is given in the question as positive, so the little q's must be negative. So must have, we must have q equals minus q, or q negative, in other words. So the particles must be negatively charged. If they're negatively charged, then our r's would be positive, and it would be given by this value. Okay, so now we want to extend the system by adding little tubes. So we have our sphere, and then we want to extend outside the sphere and put the particles out here. So again, we have our sphere of radius a, and now the particles are being separated by much larger distance. And wonders if we can still do it, or they can still wait, they're still in equilibrium position. So in this case, the only difference is that, again, our E field times our area is the charge enclosed over E naught. In this case, our charge enclosed is our total charge, as at this radius we're enclosing the total charge at all times, but our surface area is still going to be this 4 pi r squared. So then our E field is just Q over E naught 4 pi r squared. And so then our force on our particles is going to be Q over 4 pi epsilon naught r squared. Okay, and then our force on our two particles is still going to be the Q squared over 4 pi epsilon naught times 2r squared, summing our two forces and setting the acceleration to 0. To r squared is equal to 0. Will allow us to solve this here, or solve for the equilibrium. Again, we can cancel 4 pi epsilon naught, and now and one of the q's we can rearrange here. So we've got minus q over 4r squared is equal to q over r squared. So then the r squares will cancel, and that means then that there's an equilibrium at any r as long as q equals 4q minus. So as long as our charge is minus 4 times the total charge, there's an equilibrium at any r. So you can put the particles literally anywhere, but the charge in the tiny particles has to be 4 times that of the charge in the whole surface. Okay. Checking through the solution here. So we get that our R is minus Q. Oh, I guess I could have brought the A out. Oh, I did drop the 4, my apologies. So that 4 just kind of disappeared. So there should be a 4 here and a 4 here. So I dropped the 4 right at this point here. So yeah, it should be QA cubed over 4Q. So that looks good. So they just brought the A out, which I could have done. So this would be minus Q over 4Q to the 1/3 times A. So that's doable. So that at least there's different R's depending on the charge. And then down here, we get that there's any equilibrium at any position as long as Q is minus 4Q. So that looks good. Okay. Okay, so here we've got two particles separated by a distance di, or just d. Two particles, Q1 and Q2, separated by a distance d. I'm assuming it's along the x direction. And I'm assuming that this is my x equals 0. And so they give me that my potential is 0 at x equals d over 4. So we need to locate in terms of d any other point on the x-axis at which the electric potential due to the two particles is 0. So my potential due to a charge q along the x direction is going to be, well, don't really need that, is going to be 1 over 4 pi epsilon naught q over r. Now, my r is, remember, is a magnitude vector, or a magnitude of a vector, I should say. So it's the magnitude of a vector. So if I'm only looking along the x direction, then I could say that my potential is q over x, like that. Now, my R1 is going to be x minus 0, as it's at the origin. So then my V1 is just 1 over 4 pi epsilon naught Q1 over x. Whereas my R2 is D minus x. So then my V2 is 1 over 4 pi epsilon naught Q2 over D minus x, again absolute value. And now we're given that our V total is 0 at D over 4. I should say x equals D over 4. So then our V total is V1 plus V2, which is 1 over 4 pi epsilon naught D1 over x plus V plus 1 over 4 pi epsilon naught Q, geez, I'm messing everything up here. So this is Q1 over x, sorry, and Q2 over absolute value D minus x. Okay, so we're given that our V total at D over 4 is equal to 0. So that's 1 over 4 pi epsilon naught Q1 over D over 4 plus 1 over 4 pi epsilon naught Q2 over D minus D over 4. And I've changed these absolute values to brackets because I know that neither of these are going to be less than 0. So it all equals 0, so we can cancel these 1 over 4 pi epsilon naughts and get 0 is 4q1 over d plus d minus d over 4 is 3d over 4, so 4q2 over 3d. We can cancel our d's and say that 4q1 is equal to minus 4q2 over 3. Again, cancel the 4's. So q1 is minus q2 over 3. So we've solved for our charges, or at least our charge ratios. And now if we want to know if it's 0 anywhere else, so our V total is 1 over 4 pi epsilon naught q1 over x plus 1 over 4 pi epsilon naught q2 over d minus x. Now I want to know if this is 0 anywhere else. So again, we can cancel the 4 pi epsilon naughts. We know that q1 is minus q2 over 3. So 0 is minus q2 over 3 absolute value x plus q2 over absolute value d minus x. So we can cancel our q2's now. And so then this is going to equal 0 wherever 0 equals minus 1 over 3 absolute value of x plus 1 over absolute value of d minus x. Or wherever 1 over 3 x is equal to 1 over d minus x. So we can invert these and say that 3 times the absolute value of x is d minus x. And so now we can get rid of our absolute values by considering the positives and negatives. So if we have 3x, so this is true wherever 3x is d minus x, or where 3x is minus d minus x, or x minus d. So now we can solve for this here. So if d is equal to 4x, or x equals d over 4, then it equals 0. So we knew this one. But the one we didn't know is over here. So if this is 2x equals minus d, or x equals minus d over 2. So that's the one we didn't know. So it also equals 0 at x equals minus d over 2. So that would be looking at our figure, wherever this is. So over here somewhere. V equals 0 here. Okay, so that's, there we go. So now going through this, q1 and q2 are the same sign. Are both positive. So that's not true. None of this is true, so this is just incorrect. Okay. Okay, so we have a non-conducting spherical shell. With an inner radius of 4.1 centimeters and an outer radius of 7.8 centimeters. And there's charge spread non-uniformly through its volume between its inner and outer surfaces. The volume charge density rho is the charge per unit volume. So for this shell, rho equals B over R, which is 3.8 times 10 to the minus 6 coulomb per meter squared over R. So what is the net charge? So if we look at some R in the shell, then at that R, our charge is going to be let's try this again. Our increment of charge is going to be the charge density times the increment of volume. The increment of volume is going to be, so if we look at some small shell, right, then it has a thickness of dr and a surface area of 4 pi r squared. So it's going to be 4 pi r squared dr. So whatever the rho is at that r times our surface area times our dr thickness. So then our total charge is then the integral of this expression from RA to RB. And now our rho actually depends on distance, so that's 3.8 times 10 to the minus 6 coulombs per meter squared, integral RA to RB of 1 over r times 4 pi r squared dr. So we can bring out our 4 pi. And then cancel one of the r's, so it's RA to RB of r dr. And now our integral rules, we just raise the power by 1 and then divide by the factor. So r squared over 2 from RA to RB. So we get 2 pi and so then that's RB squared minus RA squared. And now our RB is given in the question as as 7.8 centimeters, so that's our outer radius, times 10 to the minus 2 meters squared, minus, and then 4.1 centimeters is our inner radius. And so this comes to 1.051 times 10 to the minus 7 coulombs. So that's our net charge in our shell. Checking the solution here. Do our integrals. And it comes out to 0.105 times 10 to the minus 6 or 1.05 times 10 to the minus 7. So looks good. Okay. All right, so here we've got a cycle. So first we undergo compression from a pressure and a volume to another one. So if we draw this here on a pressure volume plot, so we start off at, and so PV is constant. So first of all, I'm just going to convert these units. So it's 10 pounds per inch squared times 4.4482 newtons per pound times 12 inches per foot times 1 foot per So that's squared. 0.3048 meters squared. So this comes out to 68947.238 pascals. And our pressure 2 is 344,736.189 pascals. Yeah, okay. Okay, so then, and our volumes, our V1 is 4.0 feet cubed times our foot conversion here, which is 0.1133 meters cubed. So our second volume then, so PV is constant, so P1 V1 equals P2 V2. So then 68947.238 pascals times 0.1133 meters cubed over our second pressure, 344, is equal to our second volume. So our V2 is 0.0227 meters cubed. Okay. So now we've gone from a larger volume and a smaller pressure to a larger pressure and a smaller volume. And then so we're compressing, and then we're going from we're maintaining the pressure to bring the volume down, and then we're going back, maintaining the pressure. So constant volume here, but changing the pressure, and then bringing the pressure of the volume back under constant pressure. So here is constant volume, and here is constant pressure. There. Okay, so then for this first one, our work, so our work is always minus P dV. So our PV is a constant, or our pressure is our constant over V. I'm going to go ahead and just call this constant C, so I don't have to write C all the time. So C over V. So our work is minus C dV over V. So then our work is the integral of this expression, so minus C integral of dV over V from V1 to V2. So minus C ln V from V1 to V2, which is minus C ln of V2 minus ln V1. Which from ln rules we can write as minus C ln V2 over V1. And again, using ln rules, so negative of a ln, you can just flip them. So it's just C ln V1 over V2. Now the value for C we can just use our P1, V1. And write it like that. As our C, we could use really any pressure volume. So we could have used P2, V2, but might as well just use those. And so then it's 6, 8, 9, 4, 7, 2, 3, 8 pascals times our initial volume times the ln of our initial volume over our final volume, which comes out to be 12,558.704 joules. So there's our work in that compression. So that's 1 to 2. So for 2 to 3, dV equals 0, as we're under constant volume. So our work is 0. And then for 3 to 1, we're under constant pressure. And that pressure is our initial pressure. Wait. Did I not convert P2 right? Oh yeah, okay. Ugh. Is our initial pressure. So that's the so our work is minus P delta V, which is our minus 68947.238 pascals. Our delta V is 33 meters cubed minus 0.0227. So that's our final minus our initial. So that's minus 6,246.62 joules. And then, so that's the work done in each process. And then our total work is 12,558. So there's our total work done. Okay, so checking through the solution here. Oh, they left everything in pounds and feet. So I can really just say, looking at the expressions, so there's our constant temperature work. So that is the same expression as if PV is constant. Then it would either be P2 over P1 or V1 over V2, which is what we used. The work in the second process is 0. And then in the third process, we just have PV work. Now this should be minus PV, not positive, so it actually wouldn't sum up. So work in third process should be negative. So or should it? No, because it's expanding. No, that's not correct. My bad there. Yeah, it shouldn't freely expand, so that actually might be my bad there. Work. This is it should be minus P delta V, or is it actually just P delta V? Ugh, I've got myself confused here. So the work. So delta U should be minus F dx, which is minus our force over our area, which is our pressure, times our dV, so minus P dV. Right, okay, my apologies. So the work should be minus delta U, so it should be plus, sorry. So that would be plus. And then this would be the sum of those two. So yeah, so that's right. So it should be plus P delta V. So that does look good then. Just some unit stuff. Okay. Okay, so so here we have a triangle. So there's a theta, our alpha, those are 90 degrees, that's A. So A is 12.6 meters, our B is 8.22 meters, our alpha is 50.6 degrees, and it wants us to find theta. Okay, so then this side here can be gathered with, so tan alpha is equal to, I'm going to call that C over A. And then from the theta triangle, we can see that sine theta is B over C. So then from this expression, we can solve for C as A tan alpha. So then sine theta is B over A tan alpha, which is 8.22 meters over 12.6 meters times tan of 50.6 degrees, which is 0.53587. So then theta is equal to 32.403 degrees. All right, so there's our theta. Okay. So this one here, we've got 4.8 kilogram weight. Which is sliding down a 22-degree incline. Let's try a bit better. Okay, so we've got our weight. And it's attached to a pulley, which is attached to a cylinder. And then the pulley is a disc of 4.5 centimeters and mass 0.55 kilograms. And the cylinder is radius 9.4 centimeters and mass 8.6 kilograms. Okay. And it wants to know find the velocity after it has traveled a distance of 15 centimeters down the ramp. So we need to, first of all, we need to figure out what the acceleration is. So looking at this system, we've got a few free body diagrams to draw. So starting with our mass, setting this as our x and this as our y. And there's no friction, so that's okay. So we just need to worry about our mg, and that's going to be 22 degrees. And so just looking at our x direction here, we've got mg sine of 22 minus our tension is equal to our ma. Now this acceleration is going to be the acceleration of the string in the entire system. But there's our, and I'm going to call that T1. Just differentiate it everywhere here. So we've got T1, T1, T2, and T2. Okay, so now looking at the pulley, so our pulley has a T1 and a T2. First of all, so we've got some torques. So first of all, our moment of inertia for a disk is 1/2 its mass times its radius squared. So our torque 1 is going to be T1 R pulley. Now the direction is going to be by the right hand rule, and since we've got our x axis going this way and our y axis going this way, this will be, and I want to make sure I don't mess this up, a negative torque. And our torque 2 is going to be T2 times our distance. Again, using right hand rule. So the torque is going to the right. Oh, sorry. So our torque 1, our RP, so this is actually a positive torque, and our torque 2, and our RP makes that a negative torque. And then our alpha is spinning clockwise, or as long as we're assuming an alpha clockwise. So then our torque 1 plus our torque 2 is our I alpha. So then we have T1 minus T2 RP is 1/2 MP IP alpha. 1/2 MP RP squared alpha. We can cancel one of these RPs and say that T1 minus T2 is 1/2 MP RP. So alpha is our acceleration over r squared, or over our r, sorry. Right, so just as omega is v over r, our alpha is a over r. And this acceleration is the same acceleration as we saw as we saw in the previous, right? Because this is going to be, our entire system is going to have this acceleration, so a over rp. And so it's 1/2 mpa. Okay, and now if we look at the hoop, so we've got this expression relating our tensions, and we've got this expression relating our tension to our acceleration. And now if we look at our hoop, now we have just one torque, just tension 2, and there's our RC. So now we have RC T2. Looking at using right-hand rule, we see this is a negative torque, so our torque is minus T2 RC. Again, having our XY axis go this way. So then this equals our I alpha. In this case, our I for a cylinder is just mcRC squared. And again, our alpha is going to be our acceleration over our RC. So then the only difference here is now our hoop is now going to be traveling in the counterclockwise direction, not the clockwise direction. So our alpha is actually our minus our acceleration over our RC. As we've reversed the direction of our travel here. So it's minus T2, RC is minus MC RC squared times the acceleration over RC. We can cancel. And so then, and this goes here, so T2 is MCA. Okay, and then from our pulley expression, we have that T1 minus T2 is 1/2 MPa, or so now we can say that T1 is 1/2 MPa plus T2, which is 1/2 MPa plus MCA. Okay? So now we have T1. And now going back to our original expression, we have mg sine of 22 degrees minus T1 is equal to m weight A. So now we can plug in our T1 and say that mg sine of 22 degrees minus mp over 2 plus mca is equal to mwa. Bringing this to the other side, we can say that mg sine of 22 degrees is equal to A times the mass of the weight plus the mass of the pulley over 2 plus the mass of the cylinder. And we could say finally that our acceleration is mg sine of 22 degrees over the mass of the weight plus the mass of the pulley over 2 plus the mass of the cylinder, or it's equal to 4.8 kilograms times 9.8 meter per second squared sine of 22 over the mass of the weight is 8.6. Mass of the pulley is 4.8. Or mass of the cylinder, sorry, is 4. What did I do here? Mass of the cylinder, that is the mass of the weight, and the mass of the pulley is 0.55 over 2. Sorry, I kind of swapped those. And if we do this out on our calculator, we get 1.2886 meters per second squared. And now finally, we've got our acceleration. So now we're in a place to just do some basic kinematics. So xf is xi plus v naught t plus 1/2 at squared. And so then if we start from rest, v naught is 0. We're starting at 0. So then our t is our square root of 2xfa. 2xf over a. I'm just going to expand this so it's more obvious. Okay. And then our VF is VI plus AT. So dump that. So our VF is just A times square root of 2xf over A, which is the square root of 2axf. So 2 times our acceleration we just solved for. What am I doing? Meters per second squared. Times our xf, which is 0.15 meters. And this comes out to be 0.6218 meters per second. Okay. So then going through all this, we get down to the solution, which is 0.62. So that looks good. All right. And I'm going to stop it there and say I hope you enjoyed this. If you did, please subscribe to OneClass. If you want to ask questions, please follow the comments or the links below the videos. This has been Jeff Krause for OneClass, and I hope to see you again.